next workshop is with Julia Oliveri. She's a PhD student at Stanford University. And Julia is a third-year PhD student in the Institute of Computational and Mathematic Engineering. She's currently working with Professor Julia Salzman to develop robust statistical tools for analyzing alternative splicing from single-cell RNA sequencing data. Julia will be online, available to answer your questions during her workshop, Graph Theory for Data Science, Part 1. What is a graph and what can we do with it?
Hi, my name is Julia Oliveri, and today I'll give you a brief introduction to graph theory. We'll start by talking about why graphs are useful. We'll go over some basic definitions, and then we'll talk about some ways we can quantify and categorize graphs. So this workshop is the first in a 3-part series. So next time we'll build on what we learned today by exploring some of the most common graph algorithms. And then in the third workshop, we'll explore attributes of graphs based on real-world data sets. So if you're watching live and have any questions, feel free to put them in the chat. And if you're watching after the fact, you can email me with any questions or comments. So let's get started. Okay, let's back up for a second and think about what a graph is. A graph is basically a way of depicting relationships between things. So, for example, like when I say things, they can be anything. Items, people, places, abstract ideas. So if you have a group of things and then relationships between them, you're essentially making a graph. So for example, a family tree is a graph because it maps the connections between members of a family. And a map is a graph because it maps connections between places. So when we work with big data, there are many situations where we want to keep track of relational data. So for example, Google uses a knowledge graph to help with their search functionality. So when you search something, you don't only want to search exact string matches, you also want to find related concepts. So Google has what's called a knowledge graph, where different things and concepts are connected to each other. So for example, the Mona Lisa is connected to the Louvre because it's found in the Louvre, and it's connected to Da Vinci because Da Vinci is the artist. So if you search for the Mona Lisa on Google, you might also find information about the Louvre or Da Vinci because they're related concepts. So graph representations are useful in every field. So for example, in biology, this is an example of a graph of gene regulatory networks. So each dot is a different gene, and there's a line between them if the genes regulate each other. So just based on looking at the structure of this graph, we can see that there are some genes that regulate many others. So they're kind of like clusters of co-regulated genes. And now we'll talk about one more example before we move on to some definitions. So this is a graph depicting different academic papers. So this paper in the middle is the initial paper that came out in 1970 that introduced ridge regression. And there are connections between papers if they cite each other. So we can see that in the 1970s and 1980s here, There were a bunch of papers that cited the ridge regression paper and cited each other. And then in the early 2000s, there was another group of papers that were all citing the ridge regression paper and citing each other. But these two groups were separate fields. So they're both related to the ridge regression paper, but we can see just based on the structure of this graph that they weren't connected to each other. So now let's back up for a second and think about what a graph is. So a graph is so now that we've seen these examples of how graphs are useful, we're going to talk about the general definition of a graph. So let's define a graph G as a set of vertices and a set of edges with two properties. One, V is finite and non-empty. And two, each element of E is a two-element subset of V. So here we can think of V, the set V, as kind of our things that we're going to connect, and then the set E represents the relationships between those things. So we also often call elements of the set V vertices or nodes, and we call elements of the set E edges. So let's look at an example. If we let V be the set A, B, C, D, and E, these are our five things. And then with E, we're going to encode relationships between those things. So maybe A is related to B, B is related to C, B is related to D, and D is related to C. Now, this information that I just wrote down completely determines the graph. But it's usually more intuitive to think about graphs when we draw them. So when we draw graphs, we usually draw vertices as circles, and edges as lines between those circles. So here there's an edge between A and B, between B and C, between B and D, and between C and D. So this is a representation of our graph. And it doesn't matter how you draw a graph. You can put the vertices in different places. The edges don't have to be straight lines. So there are multiple ways to draw every graph. So for example, here, this graph with 4 vertices, we can see these two edges are crossing. We know that there's not a vertex there, so there's not a circle, so it's important to have that distinction. And we could also draw, that graph is equivalent to this one. There are still the same connections between vertices. We're just drawing it a slightly different way. And that's equivalent to this graph. So try to convince yourself and see that each one of these graphs is actually encoding the same information. Each one has 4 vertices and then an edge from each vertex to every other vertex. And you can see the first way I drew it includes 2 edges that are crossing, whereas the other 2 ways I drew it, none of the edges are crossing. And a graph that you can draw without any of the edges crossing is called a planar graph. And if you're interested in a bit of a challenge, try to find the smallest graph you can, so the fewest number of vertices and the fewest number of edges that you can't draw without at least 2 edges crossing. Okay, so now you might also notice that in these graphs that I was just drawing, I didn't label the vertices. So in our first example, we have labels A, B, C, D, and E. Sometimes we don't have any distinguishing information between different vertices, other than just their connections to other vertices. So when we don't have any distinguishing information, those are called unlabeled graphs. And when we do have distinguishing information, they're called labeled graphs. So this is a labeled graph, and these are unlabeled graphs. And depending on our application, we might prefer a labeled or unlabeled graph. It just depends on what we're interested in. So if, for example, this top example was an unlabeled graph, then if we just erase the edge between A and B and draw it between B and E, those 2 graphs would be equivalent because you still only have one vertex connected to this triangle. But if it's a labeled graph, then it is different because the connections of A and E are changed. So now that we have some definitions of graphs, take a few seconds to try to guess the number of unlabeled graphs that are possible, so the number of different unlabeled graphs on 20 vertices. So I'll just wait a bit and try to think of your answer. Okay, hopefully you made some guess. It's actually more than 2.4 times 10 to the 34th. It's a huge number of graphs. So even though graphs have a simple definition, there's so many possibilities, even for a small number of vertices, that analysis of graphs can get pretty complicated pretty quickly. So now we're going to talk about one of the most important families of graphs, which are trees. But to do that, we have to go over some more terminology first. So I'll just redraw our example graph here. Okay. So a walk on a graph is a sequence of vertices connected by edges. So, for example, A, B, C, D defines a walk on this example graph. And how you can think of a walk is if you start and at any vertex on a graph and then follow edges, you're defining a walk. So for the one we just wrote, we go from A to B, then from B to A, then from A to B, then from B to C, and then from C to D. So that's a walk on the graph. Now, a trail is a walk with no repeated edges. So our previous definition of a walk, we repeated the edge AB several times, so it wouldn't count as a trail. So if we remove those repetitions, A, B, C, D defines a trail on the graph. So A to B, B to C, and C to D is a trail. So a trail, you can just imagine starting anywhere on the graph and walking along edges, except you can't repeat an edge. So next, we'll define a cycle. And a cycle is a non-empty trail that starts and ends at the same vertex, but otherwise doesn't repeat vertices. So if we go back to our original graph, you can imagine a cycle as, just starting at the same location in your graph and then walking along edges until you end up back at the same location without repeating vertices or edges. So if we start at A, the only edge we can follow is from A to B, but if we go from A to B, there's no way to get back to A without repeating the edge AB. So there can't be a cycle in our graph that contains A. If we start at E, there's no edge we can follow. And because a cycle is a non-empty trail, that means there can't be any cycle in our graph that contains E. But if we start at any of the vertices in the center of our graph, for example, B, we can see that we can follow along in a circle to end up back where we started. So there's one cycle in our graph that includes B, D, and C. So we could write that as B, C, D, B. Now, a graph is connected if you can reach any vertex from any other vertex by walking around the graph. So in our first example, we can see that if we start at A, we can take a walk that can reach we can reach B, D, or C, but there's no way we can reach E from A. So this graph actually isn't connected. But we can define the number of connected components of a graph by the number of basically separate islands there are that are individually connected in our graph. So here there are two different connected components in this graph. So now we finally have enough information and enough definitions to define a tree. So a tree is defined by two things. A tree is a connected graph that doesn't contain any cycles. So to get some intuition for the properties of trees, let's look at a few examples and a small number of vertices. So if we only have one vertex, there's actually only one possible graph because there aren't multiple vertices that can be connected by edges. So this is the only graph and the only tree on one vertex. If we have two vertices, then the trees need to be connected. So we draw a line between them, and that's the one tree on two vertices. If we have three vertices, again, our graph needs to be connected. So we have to connect these two components, and then we have to add a connection to this third vertex. But if we add the third edge, then we would form a cycle in our graph, and that wouldn't be a tree. So this is the only tree on three vertices. So on four vertices, there are two different trees. We can either just have like the straight line tree, where we connect them all in a row, or we can have one vertex in the center connected to every other vertex. So just to help with your intuition, why don't you try for a little bit to draw as many different trees on 5 vertices as you can. Okay, so there are actually 3 different trees on 5 vertices. There is just like the straight line again, to connect all the different vertices. There's one vertex in the center, connected to every other vertex. And then when we have a little kind of fork in our graph, and then a straight line coming out of it. So obviously the number of trees on a given number of vertices increases as the number of vertices increases, but there are many fewer possible trees than there are total possible graphs for the same number of vertices. And another interesting fact about trees is every tree, a tree on n vertices will have n-1 edges. So when we have one vertex, we have 0 edges. 2 vertices, we have 1 edge. 3, we have 2 edges, etc. And if you're interested, you can try to prove this, or look up a proof, or email me if you're interested. But that is a fact about trees that can be very useful. So why is this subset of graphs interesting? Well, it turns out that many graphs that we're interested in are trees. So, for example, the file system on your computer will be a tree. Because, let's see. If you have a subfolder, that's never going to contain a higher level folder. Like your videos folder can't contain your desktop folder. So you'll never have any cycles in this graph, and it's all connected. So it technically is a tree. Also, like the phylogenetic tree of life, the evolutionary connections between species is a tree. So again, because everything evolves in a sequential way, you can't have a descendant then, give birth to one of their ancestors. So again, we have an acyclical tree structure. And so in general, any data that's hierarchical can be represented as a tree. And there is data that can be represented as a tree that's not hierarchical, but there are just many applications where the tree structure is appropriate. And it's useful because since trees have such a specified structure, they're often easier to prove things about, and algorithms that would take a long time just on arbitrary graphs, often there are sped up versions that can work on trees. And trees come up in many different graph algorithms, and you definitely may have come across them before. So they're useful to know about. So now we'll talk about some more aspects of graphs and some terminology that can help us quantify their properties. So first, a subgraph of a graph G is defined by its vertex set. It's a graph that its vertex set is a subset of the vertices of the original graph, and its edge set is also a subset of the edges of the original graph. And the caveat here is that for an edge to be in the subgraph, both the vertices corresponding to the edge must be in the subgraph set of vertices. So in our example from before, we could define a subgraph by taking maybe just vertices B, C, and D, and then maybe our set of edges, we would only take the edge B, C. So that would define this subgraph of our original graph. And similarly, a related concept is an induced subgraph. And an induced subgraph is like a subgraph, except you only need to specify the subset of vertices, and then the subset of edges, the set of edges for the induced subgraph is just all edges that involve those vertices from the original graph. So, for example, if we had our subgraph defined by the vertices B, C, and D for this graph, our induced subgraph would include every edge between them because they're all present in the original graph. So when we're looking at large graphs especially, it can be useful to pay attention to subgraphs or induced subgraphs of them because they can be a smaller sized and just encode specific information in our data. So another important concept is the degree of a vertex. And the degree of a vertex is the number of edges connected to that vertex. So in our example graph here, we can see that vertex A has one edge connected to it, so it has degree 1. B has 3 edges connected to it, so it's degree 3. C has 2 edges, so degree 2. D has 2 edges, so degree 2. And E has 0 edges, so it's degree 0. And degree is another important concept for graphs because we might want to find the highest degree vertex in our graph. You can imagine if we're working with a social network, for example, the highest degree vertex might correspond to someone, the person who has the most friends in the social network. Or if we're looking at a graph representing citations between papers, the vertex with the highest degree might be a very influential paper because it's been cited the greatest number of times. And An interesting fact about degree, the degree of a graph is the sum of the degrees of each of the vertices will equal 2 times the number of edges. So if you're interested, you can try to think about why that is. And if you're stuck, you can look up a proof online or email me, and I can let you know the explanation. So another important concept is a complete graph. And a complete graph on n vertices is a graph that contains an edge between every pair of vertices. So, for example, if we just have one vertex, no edges are necessary, this is a complete graph. For 2 vertices, this is a complete graph. For 3, we again draw edges just between every pair of vertices. 4, we do that again. So for a complete graph, every vertex will have degree n minus 1 because it's connected to all of the other vertices. And we call the largest subgraph of a graph that's complete a clique. And it can be interesting to find the largest clique in any graph that we're analyzing. For example, if you're looking at a social network, the largest clique would be the largest group of people that all know each other. So it can encode some important structural information about graphs. So now I'll talk about one more family of graphs that comes up a lot and is important to know about. So these are bipartite graphs. And a bipartite graph is a graph whose vertices can be partitioned into 2 sets. We can call them U and V. So the full set of vertices is the union of U and V. Such that there are no edges within the set U or within the set V. So you can think of it as 2 sets of things that can be connected between each other, but not within that set. So for example, if Netflix was making a graph of users and which movies they were watching, that would be a bipartite graph, because there would be a connection just from a user to a movie, but there wouldn't be connections between users or between movies. Another example would be if a school was making a graph of students and which classes they were taking. Because again, there won't be edges between students or between classes, only from students to classes. So bipartite graphs, again, are useful, kind of similar to trees, because there are many situations in which our data just naturally fits into the form of a bipartite graph. And because they're so specific, many algorithms that would take a long time on arbitrary graphs are a lot quicker and more optimized on bipartite graphs. And again, it's easier to prove things about them. So now we're going to talk about some a bit more in-depth properties of graphs and their computational complexities. So I'll define two separate ideas. A maximum matching first. So a maximum matching, when we're trying to find a maximum matching, we're trying to find the largest set of edges in a graph such that no two edges share a vertex. So what a matching is doing is essentially dividing a graph into pairs. So you have all your items in your graph, all your vertices, and you just want to get sets of pairs of vertices that are connected by an edge. So, for example, let's say we decided to choose this pair of vertices as an element in our matching. They're connected by an edge, so that works. But there's no other matching that we can form here. There's no other basically full edge such that neither sides of the edge share a vertex with what we've already put in our matching. So maybe there's a different way to do it. If we choose this edge to be part of our matching instead, we can see there's another edge here that, again, is a set of two vertices that are connected by an edge that don't share a vertex with what is previously in our matching. So the maximum size matching for this graph is 2. And we can see we could never match this final vertex because there are no edges attached to it. So matchings are very important and come up in a lot of different applications. So one example is, let's say you have a graph of teachers and then classes, and you draw edges between a teacher and a class if that teacher is qualified to teach that class. Maybe you want to come up with an assignment of teachers to classes so that each teacher is teaching exactly one class. And that would, to do that, you would want to find a matching between teachers and classes. So another example would be maybe you have a graph of coworkers, and edges represent good working relationships between coworkers. Maybe you're dividing your team into pairs to work on separate problems, and so you want to have a matching. You want the coworkers that are working together to work well together, and you want to find as many distinct pairs that work well together as possible. So that's another application of the matching. So another question that comes up pretty often is the question of the maximum independent set. So an independent set in a graph is a set of vertices, so rather than a set of edges, it's a set of vertices such that no two vertices share an edge. So we often want to find the maximum sized independent set. So that's just the maximum number of vertices such that there are no edges between those vertices. So in our example from before, we can, if we chose this vertex to be part of our independent set, all three of these vertices share an edge with this vertex. So we could add this vertex as well to our independent set, but we couldn't add anything else. If we instead maybe add this vertex to our independent set and this vertex, we can still add this vertex. We can see there are no edges between the vertices we've chosen. And so the maximum size independent set for this graph is 3. So the independent set problem can come up in various ways as well. So for example, if you're trying to find maybe a group of people on a team, the largest group of people who hasn't worked together before to form new relationships, if you again, have a graph showing connections between people, you can find the maximum size independent set to give you what you want. And the definitions of maximum matchings, the maximum size matching and maximum size independent set sound almost kind of like inverses of each other, right? So, the maximum matching is the largest set of edges such that no two edges share a vertex, and the largest independent set is the maximum set of vertices such that no two vertices share an edge. So you might think that it would be a similar computational complexity to solve both of these problems. But actually, it's very different. So the maximum matching problem can be solved for arbitrary graphs in polynomial time. So I think that there is a faster algorithm, but order the number of vertices squared times the number of edges, you can find a matching. But the maximum independent set problem is NP complete. So we don't have any polynomial time algorithms to solve that problem. So even though the problems seem similar, they're actually very different in computational time and in algorithms that we need to use to solve them. So it's also worth noting that if we had a bipartite graph or a tree, then there are faster algorithms that could solve these problems than for a general arbitrary graph. So that's just to emphasize the point that knowing the structures of graphs can speed things up, and also often, even if these graph problems are simple, they can end up being more computationally complex because of all of the different possible structures of these graphs. Okay, so I hope that now you have a basic understanding of graph theory and an appreciation of the basic definitions. So if you're interested in learning more, you can check back in for the next 2 workshops. And if you're watching live and have questions, feel free to put them in the chat. Otherwise, you can email them directly to me. So thank you so much for watching.